Hello grade 12s. This is the next lesson in our equilibrium unit, and again it's going to be a multiple part lesson, in this case just two. We're going to go over a few examples in this lesson, but we're not going to get into any of the math problems just yet, so just concepts to begin. And actually before we begin, let's do a bit of review. So again, this is a hypothetical generic reaction where we have reactants A, B producing C, D. The lowercase a, B, C, D are the balanced coefficients. Okay, so to review how we can put this together, we can say that the rate of the forward direction, shown here with this arrow going forward, indicating the forward direction. Just want to get my pen ready. Oh, that's good. Okay, would be then dependent according to the rate law for that forward direction. It would be dependent on the reactants A, B. Now, if we proceed, and we know that we can, in the reverse direction, then our products become what will define the rate in the reverse direction. So just a bit of review from kinetics and from our last lesson. We can then begin to write equations in the forward and in the reverse direction. Okay, yes, it's here. Okay, so in the forward direction, we know our rate is K constant, dependent on our reactant concentrations to their exponents. And in the reverse, it's dependent on the concentration of our products to their exponents. Okay, now usually you saw when we first looked at a couple weeks ago or a week or so ago, chemical kinetics, you were told that the rate of the reaction is dependent on the reactants. In the reverse direction, the products end up becoming the reactants because we're producing the reactants in that case. Because it is a dynamic equilibrium situation going back and forth. In this case, in the reverse direction, the products concentration of the products then will affect the reverse rate. Okay. At equilibrium, though, we can do something. At equilibrium, both rates are equal, so we can equate the two, and it looks like this. With a bit of rearranging from that generic equation between the reverse, and the forward rates, we can then rearrange this and it can look like this, where our products and their exponents are over, and in the numerator are then over, in the denominator, the concentration of reactants to their exponents. This gives us a ratio. Ratios tell us things. Also here, Kf, that constant, that rate constant Kf over Kr, is then going to give us a constant called, often referred to as Keq, oh, my pen is ready, or an equilibrium constant. We're going to hear that a lot. So our equilibrium constant is Keq, and that is actually a comparison, just generally speaking, a comparison of your products over your reactants. Okay, when it has a subscript as EQ, we know that value exists at equilibrium. Okay, so that comparison, we're going to compare forward and reverse, and many examples that will come forward. Okay, something else to be said. So this is our generic equilibrium law, products over reactants. Notice there's no K value, K forward, K reverse. There's our new K at equilibrium, or our equilibrium constant. A couple of things to say. There are no units for our equilibrium constant. You can figure out units. It just depends on the type of reaction this is. They're not really telling of anything. It's just that value that K has that's important, right? So no units for K. You don't have to worry about units. The other thing, as we've mentioned in the past, K is temperature dependent, right? Change temperature, it will change our value of K. Okay, a bit of math here. If this ever comes up, you just reminded that you can figure out, if you know what Keq is, its inverse is then equal to Kr. Okay, something to be said here. I know that a week or two ago, we talked about rate laws back in chemical kinetics, and we said that exponents were not equal to the coefficients, but we can say that at equilibrium, the exponents are equal to the coefficients. That allows us to take the subscripts from that generic equation way back here and use them as our exponents in our rate law at equilibrium. Okay, so first example. This is a balanced equation, famous equation, and the production of ammonia. Our numerator then is products Our denominator is then our reactants. Okay, now the complete expressions, we can say rate our equilibrium law, or no, I'll just say that. That's more accurate. Oops. KEQ, our equilibrium law, then is numerator over denominator. Okay, so this is our rate law. In this case, at equilibrium, our equilibrium law. Okay, so using an example like this, now extending that to our second example, here we have a different reaction. Here we have, I'm just going to change, I don't need a pen right now, select, okay. So here we have the production of hydrogen iodide. Okay, and it's dependent on the concentrations of hydrogen gas and iodine gas. It, of course, has a reverse reaction, you just don't have that arrow drawn. And there are different trials. It reminds you of rate law from previous lessons, but here looking at comparing now different concentrations. So originally we can say we have a concentration of our reactants at 1 mole per liter. Okay, no products, right? And in this trial, after it's reacted and it's reached equilibrium, we then have these concentrations, right? 0.22, 0.22, 1.544. Okay, now same setup here, except in our second trial we begin with hydrogen iodide, just product. Turns out then, after you let it reach equilibrium, you end up with the same. Just turns out in this case to be the same concentrations. Okay, now completely change the situation. You have 1 mole per liter of hydrogen and 2 moles per liter of iodide. Iodine gas, and 3 moles per liter of our product hydrogen iodide. Put that in the same conditions and let it react, you get these different concentrations. Now, the equilibrium constant, or the equilibrium law, is this. It's products to the power of 2 over our reactants, each in this case to the power of 1 from the balanced equation. Figure out what that equilibrium constant is, and these are our values. Turns out it's the same, right? So from all of this raw data, at three very different situations, you end up with the same equilibrium constant. Now, the question that usually comes after this is why? Explain why. What is the significance of showing you this? There was no calculations involved, just what was significant. And I've had a few classes from different semesters come up with their own note, and I've saved some of these. I'll just show you a couple here. So one class said, and this is in their own words, the equilibrium constant is the same no matter the concentration of the reactants and products. Good, so long as the conditions are the same. Another class says something very similar. Regardless of the initial concentrations of the products, of the reactants and products, the equilibrium constant will always be the same at equilibrium. Good. Others read a bit different, but essentially come up with the same important point. This group said at a constant temperature. Very good. Okay, so that I want to emphasize that's important. You're going to reach the same KEQ value regardless of your concentrations, given the same conditions. Right, so that was a big idea there. Now, just as a bit of review, back to grade 9, a homogeneous system. See how things are coming full circle. A homogeneous system is one where all your phases look the same. So very simply put, that's one phase. A heterogeneous system is one that is not. So we can extend that then to the different types of reactants and products that you might see in equilibrium problems. If you have a solid, something solid like gold, you can see that changing the amounts of gold doesn't change its concentration. This amount, that amount, a greater amount has the same concentration, the same molarity, and that's dependent on density. Let's get a pen. Okay, now if you look at a liquid like water, not aqueous, right? Water. If you change the amounts of water, different amounts, you don't change the concentration of it. It's the same molarity. You've changed the amount for sure, you just haven't changed the concentration. It has the same density no matter how much water you have. Now what's different though is if we're looking at changing concentrations, it can really only happen in a few examples. So in a few instances. So here's helium gas. In the same volume container, we have a certain amount of helium gas here, double that and then triple that initial amount in our third sample here. We can see that they do have different concentrations. Changing amounts of this gas in this case with the same volume does change concentration. So similarly then, if we have an aqueous solution, doubling and tripling concentration of sodium chloride in an aqueous solution will also change concentrations. And if we're talking about equilibrium, which involves talking about the change in concentrations, these examples, these are really the only ones we can talk about because these concentrations do change if their amounts change, whereas solids and liquids, they don't. Now, why is that important? We're going to certainly see that in a lot of detail, but first we're going to start with this. Here's an example. We have calcium carbonate, solid calcium carbonate, that when it's decomposed produces carbon dioxide and calcium oxide, otherwise known as lime. Now initially you might think, well, KEQ is going to be equal, right? Didn't he say KEQ is going to be equal to products over reactants? And look, they're all a 1-to-1 ratio here, so that should be pretty simple. You write concentrations of products, CO2 CaO over calcium carbonate, and we're done. Now, because our KEQ value is dependent on the change in concentrations, or the concentrations specifically, if we can't talk about changing concentrations with solids or liquids, then we have to get rid of them. Is my pen ready here? I do. So calcium carbonate isn't involved in our KEQ expression. Neither is calcium oxide. So the real KEQ rate, KEQ, I keep on saying rate, the real equilibrium constant K is then just dependent on the concentration of carbon dioxide. So the measure of K is only dependent then on the concentration of calcium dioxide. I said calcium dioxide, I meant carbon dioxide. Okay. So just summarizing, gases have a molar concentration, aqueous solutions have a molar concentration, pure liquids or solids, they have a constant density, so they are not involved in KEQ expressions. Okay, another example, and just to emphasize a different point here, we need to convert a molecular equation into its ions, into its total ionic equation, and then from there remove any spectator ions. So back to grade 11, going to remove whatever appears on both sides. So aluminum doesn't, copper ions, nope, they're okay. We have chlorine here, chloride, I should say, chloride there. So we're going to remove those spectator ions, and then we can say our products to their whatever exponents they have, our products over reactants is then our KEQ expression. And take a second, I'm going to actually oops, went too far. Fix this. Good. Take a second and think about, you might want to pause the video. What is the KEQ expression for this now total, or rather net ionic equation? Okay, hopefully you're at least envisioning this. KEQ is then equal to aluminum to the power of 2. Looking at our product side, you only have solid here, which is not included, and an aqueous aluminum ion. So you only include this aluminum ion to the power of 2. So concentration of aluminum to the power of 2. Then for our reactant side, well, here you have a solid as well, aluminum, you don't include that, and copper ions, AQ, so you do, to the power of 3, and that is your KEQ expression. Okay, so simply remove solids and pure liquids. The last slide, and I thought I should mention it now that we've talked more about more about KQ expressions. So if an equilibrium expression or rate, not rate constant, equilibrium constant K is greater than 1, here are your options. Which one would it be? The concentration of products is equal to the concentration of reactants at equilibrium, or the creation of products is favored, or the creation of reactants is favored, and very little products are formed. Right. So I said that K is, if you recall, a ratio. And we've already seen a few examples now that displays that, right? Where aluminum over copper at equilibrium, our K value will tell us a certain value. Now, what if that value is greater than 1, which means our denominator is greater than our, reverse, our numerator is greater than our denominator. Okay. What if K is less than 1? Our denominator then is greater. Now think about what is in our numerator and what is in our denominator. Remembering that our numerator sees our products. Okay, so if the numerator is larger, then we would have more products. So this would, hopefully you've matched this in your head, K being greater than 1 would mean the creation of products is favored at equilibrium. If K is less than 1, that would mean our denominator is greater. Our denominator represents reactants. So this would be correct here. The creation of reactants is favored and very little products are formed, relatively speaking, which only leaves us with this over here. When KQ is equal to 1, then the concentration of products are equal to the concentration of reactants. And that doesn't always happen. It often does not, but that's what that scenario would be. Right, we're going to stop part 1 of this lesson, and we're going to continue with the fun stuff in part 2.